Hello and welcome to the Omniscient webinar titled Machine Translation Primer, Current Technology and Future Directions. My name is Dion Wiggins. I'm the Chief Technology Officer for Omniscient, and I'm joined today by our Chief Scientist, Philipp Koehn, and we'll be going through a number of topics today. We'll be starting with current technology. We'll be looking at SMT very briefly, shallow NMT, deep NMT, and of course hybrid NMT. We'll be looking a little bit at domain adaptation and some of the recent research progress. From there, Philipp will take over and we'll be looking in a forward direction towards near-term things that are happening. There's quite a few major changes ahead, including deeper models, some new models from Google and Facebook, various changes in toolkits, what we've learned over the last year or two, and little bits about hardware. And then finally, we'll touch on getting back to business. What does it mean to use it in your business? If you have any questions, please feel free to submit them at any time, and we will do our best to answer the questions right at the end of the webinar. We'll save some time at the end. So let's start with current technology. So learning and machine translation. In the past, in the 70s, things were based around rule-based technology. Today, since the 90s onwards, most of the leading technologies for machine translation have been data-driven. And this has really dominated all the way from word-based, phrase-based, syntax, and today's leading technology is neural-based. The most common approach has been probabilistic estimation, and this is a diagram you'll see on the right-hand side of the screen that has been around for a long time. The key is to get from the source language to the target language, transferring semantic, syntax, and lexical information. So that starts from input analysis and then output generation on the other side. So this presentation today will go through how some of those things are achieved, both now and some of the future models. So before we go there, let's look at some of the data that's needed to teach machines how to translate. Of course, the most important data is bilingual sentences. And often these come in industry standard formats such as TMX or XLIF, and often they are sentences extracted from matching documents as well. So both statistical and neural machine translation leverages heavily bilingual sentences. Dictionaries and glossaries are very important. Now, statistical also uses monolingual data, in particular in the target language, but also for creating data using the source language. Now, neural at the moment doesn't use these technologies, but there's a lot of research in this space about how it can be used to generate new data and new bilingual data in particular. So with machine learning, the traditional approach has been you have your input, you work out what your features are through analysis, and then you generate your output. So that feature engineering is typically done by a programmer where you code a feature, and those kinds of features in machine translation would be something like what is relevant to word order or what is relevant to lexical translation or lexical transfer. With neural technologies, these features are hidden away, and the promise is that there's no more feature engineering by a programmer. Instead, the neural tools discover the features automatically and learn how to process those features to give you an output. And that's where the focus in research and both real-world applications has moved to today in many cases. So if you want to take it from a different viewpoint, this is a little bit of a cluttered slide, but it gives you a visual relationship of neural data from actual training data. And if you look a little bit closer, you'll start to see that these relationships are a bit like a human brain and they're grouping concepts together. So you can see things like growing and developing, playing, scoring, winning, losing, those kinds of things. Now, the distance from one word to another is the closeness of the relationship overall. And of course, there can be many layers to the relationship. So in this case, you have sports, which overlaps into television broadcasting and media and entertainment. So you can have a lot of those overlapping relationships that are built out. Now, when it comes to neural, we have simple neural, which we often call shallow NMT, okay? And then we have deep NMT. The difference is how many layers that the system goes down. So if you look at the shallow, which is one of the more common approaches today, but rapidly people are moving towards deep. It's a lot faster to train. It has the ability to do incremental training time in a matter of a couple of hours, and typically anywhere from 20 to 40,000 words a minute. And recent movements have got things even faster than that. With the currently released neural technologies, we're looking at about 5 days to train for deep NMT. We're looking 5 to 6 hours to do an incremental training, and the current technologies on the market are 10 to 20,000 words per minute on a single GPU. Now, when you look at quality, this is where things start to get interesting. So neural is not always better than statistical or phrase-based translation. So on very short phrases, actually statistical does better than neural. And on very long phrases, statistical does better. The other thing that statistical does better is out-of-domain content. Neural doesn't like things that are out of domain. So we came up with a solution for this, which is our hybrid NMT, where it looks first at a set of rules that say how long is the text. If it's short, go straight to SMT. If it's long, then translate with neural and look at a quality threshold. If the quality is below a certain bar, then try SMT, compare the scores, and merge that content into a final high quality output, the highest possible. And that's been working very well for a number of our customers. Now, when it comes to data, you do need a lot of data. So neural typically needs more data than statistical, and it needs higher quality data. It doesn't have the benefit of a language model, which is in statistical, which can also help improve quality a lot. That language model can only be attained by bilingual data. So we're now looking at building neural systems with many millions of segments and building it even further out. Now, that would have been unheard of just a few years ago for statistical, but that's sort of where we are today. We're heading into normal being 20 million or plus segments. Now, one of the things we've been spending a lot of time on is domain adaptation. So one of the things relating to quality, of course, is understanding context. So if I have the word virus, I need to know if I'm talking about virus in the context of medicine or virus in the context of a computer virus. Now, the way to translate that with a machine is that you build a domain relating to IT or life sciences. And building that domain is called domain adaptation. Now, generic engines like Google and many others that are out there do very well on mainstream topics, but they don't do so well as soon as you step off the side to, let's say, engineering documents or marketing or something like that. But a built-for-purpose custom engine can do very well indeed. And I'll be showing you some measurements against those. Now, one of the ways to get that data, of course, is your customer could provide the data, but there's usually not enough, especially now that we're doing neural. You know, in the past, a lot less statistical data, or a lot less data would be needed to build a statistical engine. So it's a little bit like trying to pull a rabbit out of a hat. You've got to find a way to do it. We could crawl data and then align the content, and we have tools that do that, but there's often some quality challenges there, and it's a little bit slow and time-consuming. One of the areas we're doing a lot of work in right now is data manufacturing and synthesis, but this is very complex and expensive processing. It's useful, but the data is not perfect, well, at least not yet. We're working towards getting that better and better, where we're synthesizing data from data we already had with a goal of getting many multiples of the data that's already in the domain. That shows a lot of promise. Now, when it comes to customization, here's a very simple example. This is English-Japanese and Japanese-English. And if you look at the blue scores, you'll notice some very interesting results. So Google has, you know, tens of millions or hundreds of millions, perhaps, of English to Japanese sentences. But with just 1 million sentences, we were able to beat Google with a blue score of 36 versus a blue score of 31 for shallow NMT. And on the exact same data with deep NMT, it went up 12 blue points. So you can see just with 1 million sentences of in-domain data, it makes a huge difference. Now, let's take a different comparison. In this case, we had about 12 million sentences of German, and it was in the patent domain. And Google has pretty much that exact same data. So when we built our deep engine, we did a comparison, and we found that we were about 4 blue points above Google. Now, the difference here is that while Google has the same data as us, they also have a lot more data, and that is causing confusion and ambiguous terms get mixed in, and the net result is it's not a focused domain. So Google will often translate it into a different context rather than a patent. So this is a really important difference. So more data is not always the best solution. More data will certainly give you more general coverage, but if you want a high quality engine, focusing on domain and domain adaptation is really important. With NMT, it's even more difficult than it was in SMT, and that makes a challenge for a lot of companies who in the past, many of them had done do-it-yourself SMT systems, or perhaps with Moses. This is a lot harder to do now, and you need a lot more data to get it working. Okay. Over the last year and a half, there's been a lot of research done, and we've made some really significant progress ourselves, but the industry as a whole, both academia and commercial, has made a lot of improvements. So a year and a half ago, it was taking us 4 weeks to train an engine. On that same data today, we can train that in shallow NMT in about 8 hours. And in deep NMT, we can train it in about 2 days. Whereas just last May, it was taking us about a week. Okay, in terms of translation, we've just got some new results in the last few days. So our deep NMT now is able to translate on a single GPU at 50,000 words a minute. Okay, last year, it was only 15,000 words a minute, so we've made some significant improvements. Now, in July last year, in 2016, shallow NMT was translating at about 3,000 words a minute. So that's about the same speed as SMT on a single CPU core. So we thought we were pretty fast at 35,000 words a minute, but it slowed down quite a bit when we started doing deep. But with some recent optimizations, we're now up at just under or pretty much on the mark of 50,000 words per minute. We've also last year added the ability to do forced phrases and forced translations, so things like dictionaries, glossaries, and do not translates. And we've managed to get very accurate word alignment, which is very important when you're mapping formatting from source and target to know where words moved and what happened to them. So all of these are really crucial developments that have made a significant advance. But with speeds like 50,000 words a minute per GPU, it's now actually cheaper to translate on a GPU than it is in SMT on a CPU. So I heard recently somebody saying that it was 71 times more expensive to translate. It's not anymore. It's certainly very commercially viable, much more so than SMT was even. So with that, I'm going to pass over to Philipp, and he'll take you through the next stage.
Okay, yeah, so this is Philipp Koehn. I wanted to give you a bit of a sense where things are heading in the future. What are the current developments in neural machine translation? So we just concluded another exciting year in machine translation research. We have a number of new models that were proposed that outperform what we had previously, deeper models. Google came up with a new model that I will describe in some more detail, and also Facebook came up with a new model that I'll describe. There's also a big effort to build models that take richer and wider context of their account. Models that are informed by syntax, or even that look at the entire document and take that into account when you translate. These are all kind of recent research activities. Not quite clear what will be better and faster in the future and what would really catch on. To kind of review these models a little bit, this is kind of a very colorful depiction of the kind of state-of-the-art standard approach that has dominated neural NT over the last 2 years. This is based on recurrent neural networks. If you look at the green boxes, I think one crucial thing that I'm going to draw a difference to later is that you see a lot of errors going left and right on the encoder side. The key thing here is that you take the input, encode it in some way, and then when you translate, you pay attention to part of the input. This is the attention mechanism. To refine these models, you can add more processing steps, both in the encoder, where it tries to represent the input better, and both in the decoder, where then tries to build a more complex coherent sentence in the output. This is what we described earlier as deep NMT that results in significantly higher performance. These models are more complex and they take longer to train. Here's a depiction of Google's transformer model. So what I pointed out earlier is that in the encoder layers, we had previously errors going left and right. That does lengthen the path of computation from the input to the output. That is both a computational burden as also a machine learning problem that you have to propagate knowledge from the output, where you really know the right answer all the way back to the input over much longer paths. So the idea is to take this attention mechanism and kind of drive it into the encoder and to the decoder. So the encoder, you can think about each word is refined by all the surrounding words, and that can pay attention to which words it should pay attention. It's more informed by. So the verb might not only be informed by itself, but also by its subject and its object. Another model that was proposed that had a similar philosophy last year is by Facebook. They use convolutional neural networks. These are the standard methods to do neural processing in the vision domain, where you start with a very, very large millions of pixel image, and you try to drill that down to some small information. So you always have to cluster, group information together. So they applied the same idea to neural machine translation. So you see here now that each of the green boxes that refine the representation of the input looks at the surrounding words. And if you do this over several layers, they take wider and wider context into account. So this is also faster, but it is more limited in context, so you can't have an error going all the way from the first word and the last word to any word in the middle. All these solutions are currently developed and supported by a number of toolkits. There has been releases of toolkits by all the major IT players. Google has TensorFlow, PyTorch, by Facebook, MXNet, by Amazon. These are all now deep learning toolkits that you can use for everything. There have been neural machine translation implementations for all of them. There also have been some toolkits that have been discontinued development. Ciano, which really started a lot of these research efforts a few years back out of the University of Montreal, they now discontinued development because the commercial players play such a big role in managing much better to integrate the latest features into these toolkits. Besides neural machine translation implementations based on these toolkits, there are also dedicated neural machine translation implementations. They're typically faster because they know exactly which processing steps are the most time consuming, and they can optimize, especially the way they're handled on the GPU. And generally, I have to say that there's a very quick turnaround from research ideas to deployment. Since things are often released open source, even the latest models by Google and Facebook that I talked about, you can actually download the code and try it out. I wanted to reflect a little bit where the field is going in terms of what we know, where is neural NT better, where is statistical NT better, what kind of challenges does neural NT has to really progress further down the road. So I think we can say with some certainty at the moment, in ideal conditions, meaning you have a lot of data in domain, well-behaved kind of environment, neural machine translation can achieve much better results. If you look at news translation with lots of data behind it, or limited domain translation, it's quite impressive how far we've come over the last years. Neural machine translation and statistical machine translation have different types of errors. I'll explain that a little bit longer. So there's a difference between fluency and adequacy. And generally, you find that neural machine translation is more susceptible to noise in the training data. And generally, neural NT is less robust in the sense that it deteriorates more strongly if you move out of domain or if you don't have enough training resources to train your models on. Because of these different types of strengths and weaknesses, we are betting here on a hybrid approach to combine the strength of one with the strength of the other. So here's a bit of a caricature of what might happen in neural NT and statistical NT. So if you have this input sentence, ich will Kuchen essen, I want cake eat, you really just translate it word by word, I want to eat cake. So the output you get out of statistical systems often looks like the example in the middle, I want cake eat. Yeah, something got jumbled up. The words get translated correctly, but the word order is not correct. So it's a problem of fluency. This is not a fluent English sentence, but the meaning is kind of there. The kind of worst case behavior of neural NT is that it produces really beautiful English sentences, like I want to cook chicken, that have, however, very little to do with the input. So we've seen this behavior very often when we move out of domain and also in low resource conditions. So this is when we talk about these are the areas where neural NT looks bad. These are the kind of errors you observe. These are particularly annoying errors because if you just look at the output, you think these are great translations, and you don't even realize that they have nothing to do with the input. We've done a study recently on what kind of noise in the training data harms neural machine translation. I have a bit of a summary screenshot on the right there. I just want to, probably too small to read, so I just want to give you the kind of overview. There's long been the sense that neural NT can't handle noise as well. So we really try to produce all kinds of different noise and see how neural NT versus statistical NT gets harmed by it. So we started out with a clean corpus and added noisy data to it. We kept the clean corpus size in place, just added additional noise. If you look at all these different charts and how much noise we ended, 5%, 10%, all the way up to 100%, you see in general that neural NT tends to get harmed more by noise. For instance, if you have misaligned sentences, if your sentence alignment didn't work very well, if you just have disfluent or bad language in the output, or if you have a text in the wrong language on the target side of your parallel corpus. One thing that we found extremely striking was that neural NT can get really tricked by having any kind of untranslated source text in the parallel corpus. In that case, it learns to copy just sentences from the input to the output as it occurs in untranslated text. And even if you only have small amounts, that is a behavior that it learns very quickly and then completely overdoes that. So this is a fairly catastrophic impact of that particular kind of noise. So in general, this confirms our suspicions that neural NT is more susceptible for noise. We have learned a bit more about what kind of noise, but it also drives home the point that data cleaning and clean data is more important in neural NT than it was already in statistical NT. Here's a study on out of domain and in domain. You see on the blue boxes, statistical NT, on green boxes, neural NT. So this is data sets where on some of them, neural NT is better, on some of them, statistical NT is better. They're somewhat competitive. But what you also very clearly see that when you move out of domain, when you're not on the diagonal of this chart, when you build a system on data you got out of the medical domain and then apply it to the IT domain, then typically translation quality collapses very much. So the output you actually see there is very similar to what I demonstrated earlier, that it produces, that it doesn't know what to deal with it, do in this domain, and just produces a sentence that it's seen before in its trained domain. So another thing we want to explain a little bit more, and people are very curious about at the moment, is how does neural machine translation really work? I showed you earlier kind of relatively accurate description of these models with lots of boxes and errors in between them. And as Dion also explained, the vision behind that is you just come up with a long enough computation chain and allow the machine learning to learn all the relevant features. But the outcome of that is that you don't really have a good sense of what actually happens inside these boxes. So neural machine translation is really, you take the input represented in a highly dimensional vector and have a bunch of processing steps, end up with more and more highly dimensional vectors, and then you have output. So it's a bit of a magic in the middle, and people don't have a good sense of what really happened. It makes it very hard to debug this technology or getting some insight about what future directions we should take it. So I'll highlight a few studies on the inner workings of neural machine translation models. So there's attention mechanism, word sense disambiguation, and influence of source and targets. I don't have the illustration here of the attention mechanism, so this is basically word alignment. So there's one part in the model that really does word alignment. You can look at it and you can say, oh, this word was mostly informed by this input word. Here's a bit of a clutter shot of words that occur in different contexts and what neural machine translation does with them. So one of the core problems of machine translation is obviously words that are ambiguous. Here we took the word right that has various senses. There's a political sense, right as a privilege, the right word for that, but you get the sense, right in the sense direction, right and left, right as being correct, and immediately, like right here and right there and right afterwards. And what you can see is that after several layers of processing, you see these different senses drift apart. So if you kind of see these as clusters, you see a bit of a blue cluster on the right. So that corresponds to the meaning of the word as immediate, right here, right there. While on the left, you see like a orange cluster where right as a privilege, I have the right to do something, shows up. So we do see that these processing steps do what they're supposed to do. They take a word that is very ambiguous, and after a few processing steps, looking at the surrounding context, is able to figure out somewhat better what the sense of these words are. Here's another illustration of one step in the processing further down. At some point, when it produces output words, there's always a challenge of the output word is more informed by the input or by the previous words. The challenge between adequacy and fluency. So you want to have basically produce output that is a translation of the source, but also that is fluent in the language. So the bars here, the wider they are, the more they are affected by the source. So what you see here kind of confirms our intuition, what should be happening. If you look at words like 1958 or electronics, you see wider bars there. So these are more informed by the source. While function words like comma, in, here, off, they're less informed by the content, by the input. So they're more driven by the fluency of the model. Another thing I want to just kind of add to all these developments, while all this stuff is happening, what also drives the field, of course, is better technology. Everybody kind of holding the breath about new GPUs being released by NVIDIA. So there's a new generation based on Volta technology that is going to come out. So these are faster, have more processing cores, have more memory, have higher memory bandwidth, and they will be enabling even more complex models in this space.
Okay, thank you, Philip. So going back to business just for a little bit. So we're still seeing some challenges, that's very clear. Obviously, machine translation is a long way from being a solved problem, but it is getting much better. The benefits of NMT over SMT are substantial, both in terms of speed and quality overall. If you want to use this kind of technology in business today, you can build engines quickly. It's now down to hours or a couple of days in a sort of edge case. But you need a lot more data than in your past SMT deployments. That's going to be one of the challenges going forward, is businesses finding enough data. And that's why we're putting a lot of attention into data manufacturing and data synthesis. The data preparation work is a lot more complex. It has to be cleaner. It has to be really top-notch data. So again, we're working, we've always worked on what we call clean data SMT in the past, and we're enhancing those technologies even further today to obviously leverage those into clean data NMT. And the more data that's high quality in the right domain, the better, but not the more data overall, as I mentioned earlier. General purpose engines are going to continue to improve, and we've seen engines like DeepL out there recently that are now notching ahead of Google. We'll see how long they stay ahead. That will be an interesting little race. But these general purpose engines are fine for gaming and understanding, but they're much less practical for when you want to actually publish content. When you want to publish content, you may be publishing direct raw machine translation, like some of our customers, such as LexisNexis, who are doing a very large patent project with hundreds of billions of words with us. Or, you know, if you want to do something like engineering manuals or something that's not run-of-the-mill mainstream, then you want to control writing style and you want a bit more control of what's happening to the document. That's not possible with a general purpose engine. You get what you get. So it's key. If you want high quality, you customize, and that makes a huge difference, as you saw from the metrics earlier. Now, that's affordable today. It's no more expensive than doing SMT, so it's right there, the same cost. All the complexity is being hidden away by platforms like Language Studio. Data manufacturing and synthesis approaches are going to be key as we move forward to getting these specialized domains and domain adaptation into play. Cost has come down, both in terms of hardware. So, the current hardware is about $700 US a GPU. Now, NVIDIA has released quite a more expensive one, several $1,000s just at the end of last year. That's looking promising as well, but that's a little bit out of the reach for most customers. Most people who just want to do experiments. So a lot of people could afford the lower end of that range GPU to do their own experiments without breaking the bank. But when it gets into the $3,000 or $4,000 mark, it's quite different. And that's just the GPU without all the other hardware. The pace of advancement is pretty astounding, to be honest, in the NMT space. In just 2 years, we've come a very, very long way. And as Philipp said, the speed to deployment is very, very rapid. As an example, only just the last few days, we've hit this 50,000 words a minute mark on GPUs, and we will have that deployed in a matter of a week or two into our production environment. So things are rapidly moving in that space with these new optimizations that we've done. The level of understanding compared to this time last year of how neural works and how to manipulate it and how to make it work for you has really changed and improved. The new models are interesting, but we've yet to see them really show anything better than what's currently around. That may change, but that's not yet proven. SMT is by no means dead, and if you've invested in SMT, that may still be the best solution for some of your languages. What we're doing with a lot of our customers now is upgrading SMT engines when there's enough data to hybrid neural statistical engines, and that's filling in those gaps. But low resource languages in particular, you need a lot more data to do NMT, so SMT is still going to be around for a long time to come. It's still very relevant. MT as a whole is getting a lot better. It's not a human replacement. It hasn't been, and it won't be for a very long time in most scenarios, but it enhances human productivity, and overall it provides a means to translate content that previously would not have been commercially viable to translate. So I mentioned one of our customers translating hundreds of billions of words of content using a human that would take too long and just simply be too expensive. So the bottom line is NMT is very practical to use today. The cost is no different in most cases to what you would be spending if you were doing SMT. But one of the challenges is if you're doing it in-house, there's a different cost, and that is the cost of getting the data. And that's something that makes leaving this to professionals who are skilled at building data, creating data, cleaning data at this stage. I think some of those tools may become more readily available down the road, but right now, with the volumes of data that are needed, it's less practical on that front. But in terms of the actual technology, the hardware, it's very, very affordable today. And so with that, I'm going to open up to questions. We've got a small handful of questions here. So first one for Philipp. Which domain challenges neural the most? So which is most complex, I guess you would interpret that?
I think there's not a clear answer. I think all the domains where we don't have enough training data are more challenged. So we have a lot of training data in like formal publications, IT, and news to some degree. We, for instance, don't have much data in dialogue. So any kind of system that does live chat translation is much more challenged than other domains. But that's a domain in general is a very, very complex question. We always throw that out as a concept, but it has many aspects to it. Is the style of text? Is it mostly spoken? Is it formal written? Is it more casual written? Is it things like tweets and Facebook's posts? Whenever language is not very formal, then also there are a lot of challenges. You have to deal with that. There's also the content of the language and so on and so on. So domain has a lot of dimensions. And the biggest challenge is, if language is noisy, if you don't have enough training data there.
Next question. It seems that Microsoft NMT didn't get a fair mention. Is there a reason that we're not talking about Microsoft? So I'll contribute one bit there, and then maybe Philip's got something as well. So typically when we deliver an engine to a customer, we measure against Microsoft and Google as well as our own engines. And typically in most cases, out of the general purpose engines, Google is the leading engine and Microsoft second, and usually the custom engine is notably ahead because it's very specific to that customer's purpose. However, on a small number of languages, including languages like Japanese, Microsoft often beats Google. But again, a custom engine usually always beats a generic engine.
Yeah, I didn't want to pick on Microsoft by any means. They have an excellent research team working on this, and they're also pretty much on the state of the art where everything else is.
Okay. Next question. What is the typical time frame to gather and prepare training data for a neural engine? So for our customers, depending on the data they bring us and the complexity of the domain, it's typically a couple of weeks for a professional build, maybe 2 to 3 weeks. So maybe 2 weeks of gathering and a couple of days of training. But then you have a complex customer like, say, LexisNexis, who is preparing hundreds of millions of sentences and going through many, many documents and analyzing them, matching them, and many other things. That takes a lot longer. So, but a typical engine would be 2 to 3 weeks. Now for a very long question. So let me see if I can understand this. A new successful approach to NMT has been published just before Christmas, and it's based on evolutionary algorithms. This means, in simple words, that AI designed optimize the, sorry, I can't read that, I think it's a typo. This is getting a little bit complicated. The key is, the real question at the end of this is that it requires supercomputers and HPCs to work. And as an example, they've referenced here 250,000 GPU hours. So does that possibly mean that a new era of NMT research has just begun and only research with access to a supercomputer will prevail?
So general comment there, if you design one of these neural machine translation systems, there's obviously the bulk of the parameters that you're going to train from the data. But there are also something that's called hyperparameters, like how many layers you're going to have in your deep model. Are you going to have 3 layers, 4 layers, 5 layers, which exactly kind of cell structure you have. There's a lot of these kind of hyperparameters that are kind of set by experience, and if they work, you're going to try 3 or 4 variations. So I think what this question is referring to, there are some methods to just say, well, why don't we train the hyperparameters as well? That is, of course, computationally extremely expensive, because whenever you change the hyperparameters, you still have to do the full training run of the actual system you want to build. And then you change the hyperparameters, you have to change it again. So I can believe that this takes 250,000 GPU hours to get anywhere.
Okay. So next, here's an interesting one. So we get this kind of question all the time. So what is the best BLEU score you've seen on NMT so far for French, Spanish, and French-Italian language pairs? So the issue there is it's asking a very vague question, because the test set could be different, the domain could be different, and so on. So a BLEU score isn't really relevant. Asking somebody what's your best BLEU score, we've actually got an article on that. What you need to do there is you need to focus on the comparison and the quality. Just asking a BLEU score, I can show you a BLEU score of 30 that is better than a BLEU score of 60 in a different domain, in a different language pair. So it's really important to understand what you're measuring, not just looking at the score and saying that's a high number. That particular person I'll contact afterwards, and I can run you through some of the examples we do have there. Okay. So the next one, is there a difference in the approach to post-editing when it comes to SMT and NMT?
So as I described earlier, the different kind of errors you have in SMT versus NMT. So with NMT, you're more likely to have really nice fluent output, but it might be wrong. So I heard informally from translators that translators do like that better, because they don't have to fix up all these stupid language errors anymore. And they can really focus on just fixing the 2 or 3 content errors. It does, however, require the post editor to really also pay attention to the source. So for statistical MT, we often see work patterns of translators that say, oh, that there's just disfluent translation. I fix up with disfluency, I'm done. For neural MT, you not only say, oh, it's now a fluent output, you also have to really pay attention. Was any of the content dropped? Was any of the content added? Something that didn't happen as much in statistics.
Do you envision that Google or others will end up starting with a generic engine and then on the fly switching to a domain-specific engine once context is gathered from the input document?
They haven't done that so far. They also have the very kind of sentence level focus of translation, so you can just submit a sentence, maybe a web page. So you don't really have that much document context to kind of make these disambiguation decisions. It is also very expensive to really then be prepared for a large number of different domains and switch your engine to one of them.
Okay. Here's an interesting one. How do you prioritize which data you synthesize? So, wouldn't it automatically translate training data, degrade the NMT? So one of the things with data synthesis, there is one approach where you do translate. There's other approaches where you enhance existing bilingual data by creating variants and things like that. So it doesn't necessarily degrade the quality at all. And what we've found overall is we're getting quite a bit of improvement, but we're still working on our tools to improve those further in that space. So somebody asked, what is the best practice for post-editing MT pricing for an LSP? So we have a separate webinar and a white paper on that on our website, so I won't spend time on that today, but I just wanted to point you in the right direction. Next question, and this is the last one we have on the list at the moment, so if anyone's got any more questions, now would be a good time to ask. Are there a lack of engines available for Chinese source to target at present, or is bidirectional source to target input does not matter for quality? I'm not quite sure I understand the question there. Let me try. So we're doing a number of Chinese to English and Chinese to several other languages at present, including languages like Chinese to Japanese, for example. There's certainly a gap in data coverage compared to some of the EU languages where you've got a lot of data available that crosses them all, but there is certainly data into some of the leading languages. Is there enough? I'm not sure, not readily available at least, but there'll be more coming. Okay, have you explored methods to distinguish human versus machine translation in your harvests?
So that's actually a question that has received quite a bit of attention in the research world. So it's one of these things, can we decide better what is human, what is machine? Can we actually outguess the machine? But there's actually some markers of machine translation that you can detect. It's typically much more literal. It takes much less freedoms in reordering and restructuring sentences. It also has certain behavior and the kind of vocabulary it uses. So you can actually detect that. So that's something we consider also when we do data cleaning at the end.
Okay, when we talk about 1 hour or a couple of hours for training, for how much data? So that's specifically an incremental training. And we're talking anywhere from several thousand up to 100,000 or more to do an incremental training. So this is where we would take something that we've built as a base and then add new data that we've got. So that we don't have to start training from zero, and that's one of the benefits of NMT. You can continue training from where you left off and add data. So you could have a IT domain, for example, and then add data specific to a customer and enhance it towards that customer. Okay. Has there been any improvement in terminology management for NMT?
So this is clearly a much bigger challenge for neural MT than for statistical MT. So statistical MT, we had models that we could still understand to a large degree. We still could add, for instance, translations for words and phrases, and then the engine would use them. This is much, much harder in neural MT. So somewhere in the middle, we have to manipulate the engine to say, for this particular terminology, use these translations. So this is something we have been doing for a year. It's not working as perfectly as it was previously case in statistical NT, but it's definitely a functionality also.
Okay. I would also add to that, we have the ability to push things like glossaries and forced translations into NMT when needed. So that's often very, very important for your terminology management, especially if you don't want to go retraining to add that data. Okay, how about morphologically rich languages and post-editing?
Yeah, so this is another example of where previously we were very worried about and did a lot of feature engineering, and now suddenly it's all part of the parcel of the big neural machine translation magic that we don't still fully understand. What we do observe is that the output of neural machine translation systems is generally more fluent. It can handle things that are really difficult, like long-distance relationships between words, as you see in English, in German, which has a lot of nested construction. Another big challenge, obviously, is, as you mentioned here, morphology. So having the right inflection, knowing that the last two words are actually the object, therefore they have to be in different case and different word endings. That is something that neural NT in general handles very well. I mean, it's surprising how fluent the output is in neural NT compared to statistical NT.
Right, and we've just done some interesting engines recently in languages like Finnish, which in the past has just been out of bounds for SMT. It just didn't work well at all. And the results in Finnish are very, very promising. So some of these very morphologically rich languages are now really seeing the light of day for MT when it comes through. There's a number of other questions on Blue. I'll take those up offline with the people that are asking them. But just one comment on Blue that we see consistently as well. NMT does often score lower than SMT, and we see that quite consistently, even as much as 10 or more Blue points lower. However, when a human looks at it, they like the NMT as a better translation than the SMT, even when it's a lower score. So I think it's important to understand that too, because that can often be a cause of confusion. Blue score is not the only metric. Okay, that is the last question that's left open right at the moment. So if you have any questions left, this is your last chance before we sign off for the day. Okay, no more coming through. So thank you very much for your time today, everybody. This presentation will be online tomorrow with the slides and the recording. Please feel free to share it with your friends. And if you have any questions, please don't hesitate to contact us. You can see our email, our Facebook, our Twitter, and LinkedIn all on the screen. Okay, so thank you again for attending, and we look forward to talking to you again on our next webinar. Thanks a lot. Bye-bye.